Let us start with the thing a qubit replaces, the humble bit. A classical bit is a switch. It is either 0 or 1, and at any moment it is exactly one of them. There is nothing in between, and there is nothing hidden underneath. A quantum bit, a qubit, keeps those same two labels, 0 and 1, but it stores something far richer beneath them. Instead of committing to a single label, a qubit carries two numbers, one attached to 0 and one attached to 1. We call these numbers amplitudes. And we write them alpha and beta. The state is alpha times the 0 answer, plus beta times the 1 answer. So a qubit is not one answer or the other. It is a weighted blend of both at once, and the two amplitudes are the weights.
Hold on, so alpha and beta are just the probabilities of getting 0 or 1 when you look.
That is the natural guess, and it is wrong in a way that turns out to matter enormously. Amplitudes are not probabilities. For one thing, they are complex numbers, so an amplitude can be negative, and it can point in different directions in the complex plane. A probability can never do either of those things. The probabilities only show up when you measure, and they are the squared magnitudes of the amplitudes. The size of alpha squared is the chance of seeing 0. The size of beta squared is the chance of seeing 1. And because those two chances have to cover every possible outcome, they are required to add up to 1. Written in amplitudes, the size of alpha squared plus the size of beta squared equals 1. That single equation, the probabilities must add to 1, is the only constraint we ever place on a qubit. Geometrically, it says the state is a unit vector, an arrow of length 1 living in a two-dimensional complex space. That, in full, is the definition of a qubit. Two complex numbers are hard to look at, so for the rest of this series we are going to draw them. Here is the picture we will come back to again and again, so let us build it carefully. Give each basis state its own bar. 1 bar for the 0 answer, 1 bar for the 1 answer. The height of a bar is the magnitude of its amplitude. How much of that answer is in the mix? A tall bar means a large amplitude. A flat bar means almost none.
Wait, you said the amplitudes are complex, but a height is just one number. Where does the rest of the amplitude go?
You caught exactly the right thing. A complex number has a size and a direction, and the height only shows the size. So on top of each bar, we draw a little arrow, and the direction the arrow points is the phase. Here is why the arrows earn their place. When two amplitudes land on the same answer, their arrows add tip to tail. Point them the same way and they reinforce into a taller bar. Point them opposite and they cancel out. That cancellation, two arrows pointing against each other, is interference. And it is the whole reason quantum computing is more than expensive coin flipping. Hold on to the arrows, they run this entire series. With the picture in hand, two states are worth naming right now. The ground state, plane 0, is 1 full bar over the 0 answer and nothing over the 1 answer. All of the amplitude gathered in one place. An equal superposition is 2 bars of the very same height, 1 over 0 and 1 over 1, each amplitude equal to 1 over the square root of 2, arrows aligned. Both answers weighted equally. That balanced pair is the state we are about to build, and building it takes exactly 1 gate. So how do you change a qubit? You act on it with a gate. And a gate on 1 qubit is nothing more exotic than a 2 by 2 matrix that multiplies the amplitude vector. There is exactly one rule the matrix must obey. It has to be unitary. In plain terms, unitary means it keeps the state a unit vector, so the probabilities still add to 1 after you apply it. Unitary matrices are precisely the ones that preserve length, which makes them precisely the legal moves on a qubit. The star of the show is the Hadamard gate. It is the gate that manufactures superposition out of a definite answer. Feed it the ground state, that 1 tall bar sitting over 0, and watch what happens. The single bar splits into 2 bars of equal height, 1 over 0 and 1 over 1, their arrows aligned. A qubit that was definitely 0 has become an even blend of 0 and 1. That is where superposition comes from, not from anywhere spooky. One matrix applied a single time.
Okay, but once it is smeared across both answers like that, can you ever get back to where you started, or is the zero lost?
You can get back, and how you get back is the most important lesson in this whole episode. Apply the Hadamard a second time, and let us follow each column. Look at the 1 column. It collects 2 contributions, and their arrows point opposite ways, so they cancel, and that bar drops all the way to nothing. Now look at the 0 column. Its 2 contributions point the same way, so they add, and that bar grows back to full height. The superposition has interfered with itself and snapped back to a clean, definite 0. The wrong answer canceled, the right answer reinforced. That is the entire game. Every quantum algorithm you will ever meet is an elaborate arrangement of exactly this one move. We have been pushing amplitudes around with reversible gates. At some point, though, you want an actual answer, and getting one means you measure. Measurement is where the probabilities finally appear, through a single rule called the Born rule. The chance of each outcome is the square of that bar's height. So to read off the probabilities, you square every bar. An equal superposition, 2 bars each of height 1 over the square root of 2, turns into a 1/2 chance of 0 and a 1/2 chance of 1. But measuring does something far more violent than just reporting the odds. It forces the qubit to commit. The instant you measure, one outcome wins, and every bar except the winner drops to 0. If the outcome is 0, the state becomes plain 0, and the other amplitude is simply gone. The bars collapse down to a single spike, and there is no getting them back.
Gone for good, we spent all that effort arranging the phases, and one measurement just erases them.
Gone for good. Every gate we have seen is reversible. You can always undo it. Measurement is the one irreversible step in the whole story, and yes, it throws the delicate phases away. Which is exactly why the art of a quantum algorithm is everything you do before. You measure. You steer the interference ahead of time, so that when the bars finally collapse, the answer you want is overwhelmingly the one left standing. Prepare an equal superposition and measure it many times, and you get roughly half zeros and half ones. Measure it just once, and you get a single definite bit, and the superposition is over. Here is the part that should feel like a curtain being pulled back. Everything we just drew, the bars, the arrows, the interference, is a few lines of NumPy. A qubit state is a length 2 array of complex numbers. The ground state is a 1 followed by a 0, all of the amplitude sitting on the 0 answer. That array is the qubit. Nothing is hidden behind it. A gate is just a 2 by 2 array. The Hadamard is a small matrix of ones, with a single -1 in the corner, divided by the square root of 2. Applying it to the state is one matrix multiplication. Ask for the probabilities, and you simply square the magnitudes of the amplitudes. That is the entire core of the simulator, and there is genuinely no machinery underneath it that we are hiding from you.
So that is really all of it, 2 numbers and a 2 by 2 matrix, and I could type this out myself.
For a single qubit, that is really all of it. A state is 2 amplitudes, a gate is a small matrix, measurement squares the amplitudes and collapses them. You could write it in an afternoon. But 1 qubit is a small world. The real strangeness begins the moment you add a second one. 2 qubits do not carry 2 separate blends. They carry 4 amplitudes at once, one for each of the pairs, 0, 0, 0, 1, 1, 0, and 1, 1. And some 2 qubit states flatly refuse to be pulled apart into a story about each qubit on its own. That refusal has a name: entanglement. And it is where we go next. 1 qubit is 2 amplitudes, 2 qubits is 4, and that quiet doubling is a promise that things are about to get very, very big.